Let's get started, and please welcome our first speaker, Justin Drake, on stage.
Thank you, Kartik, and good morning, London. I guess I'm based not too far in Cambridge, so feel free to say hi if you're passing along. So today I'd like to talk about Ethereum sharing, and this is the context of chains using infrastructure or reusing infrastructure that Ethereum provides. So you can have shared settlement, you could have shared data availability, and these are things that we're very familiar with in the context of rollups. But it turns out that we can go much further. We can have shared sequencing and shared execution, and these are kind of mental unlocks that I hope to communicate today. And by the way, this image here is this meme of the united chains of Ethereum, right? The closer we are, the more integrated we are as L2s, as rollups, the more network effects we will have. And the more we share, the greater these network effects will be. So first of all, I kind of want to recap some of the existing sharing that's being done today, and kind of give you an overview of the opportunity. And then I want to dive into two specific types of sharing, which is not being done today, but it's an opportunity for the future, specifically shared sequencing and shared execution. So if you're a chain today, you basically have options to you. Whenever there's an Ethereum module, you have the option to share this module with other chains or to just go your own way. And today I want to try and convince you that oftentimes sharing is maybe the right direction. And what are some of the benefits of sharing Ethereum infrastructure? And it basically boils down to inheriting some of the fundamental properties of Ethereum layer 1. You start inheriting security, inheriting the credible neutrality of Ethereum, and also inheriting the liquidity and network effects. And that's as opposed to introducing new security assumptions and falling down to some sort of weakest link, introducing new brands that has maybe less Lindy, and also just creating new boundaries and frictions that break down network effects. So what are the key modules within Ethereum? The way that I think about it, the four basic ones are settlement, data availability, sequencing, and execution. And in some sense, sequencing and execution are these new ones. Now, for settlement, we're all familiar with this. If you settle on Ethereum, you become an L2. That's a very simple definition of what an L2 is. If you choose to not settle on Ethereum, then you're an L1. You're kind of separate from Ethereum. And in terms of data availability, you also have a choice. Either you consume Ethereum data availability, in which case you become a rollup, or you choose to not consume Ethereum data availability, in which case you become a Validium. And it turns out for these two other modules, there's a similar concepts. So for sequencing, you can either be a based L2 or base rollup, or you can choose to be an independent L2 or an independent rollup. And for execution, we're just introducing new terminology here. Basically, is you can be a native rollup or native L2, or you can be a custom L2 and rollup. I'm going to talk about that a little bit more. Now, I also have some emojis here. So the scrolls can be rolled up, the way we have the scroll, based with the sunglasses and the crown. And I think what we're going to move towards is this world where we have all three. So native-based rollups. And I guess you could call them ultrasound rollups, maybe. Now, there's all sorts of downstream consequences to reusing some of these Ethereum modules. So if you use Ethereum settlement, then now suddenly you have your settlement contract on L1, and you can start composing with other contracts that are on L1. And so you can start using ETH as money. You can start using assets as collateral, and so you start benefiting from the economic bandwidth. You're kind of economically plugged in, and this is a great advantage that we all know and love. Once you start also using data availability, you start benefiting from finality and liveness. So this boils down to security properties, and you start benefiting from the economic security of Ethereum, which, by the way, is on the order right nowadays of $150 billion. more than an order of magnitude greater than Bitcoin. And then if you choose to use Ethereum sequencing as a module, then you start benefiting from things like Synchrony. So settlement here gives you asynchronous composability, but once you also use Ethereum as a sequencer, you have synchronous composability, which is a stronger form of composability, which has fewer boundaries, and I'll talk about that. And that gives you shared liquidity, for example. So one of the applications is a Uniswap or Matcha that works across all the rollups, right? Or, 1 inch, for example. So if you go on 1 inch, it will try and get liquidity from all the L1 dexes, but it won't get liquidity from rollups. And that's because there's like these strong asynchronous boundaries, and that's the kind of boundaries that we can destroy with shared sequencing with the L1. And another really cool thing is this idea of shared pre-confirmations. So right now, if I have a transaction on Arbitrum, I get a pre-confirmation from the Arbitrum sequencer. If I send a transaction to Optimism, I get a pre-confirmation from the Optimism sequencer. And these are separate counterparties that I have to deal with. What if instead there was one counterparty that could provide pre-confirmations for all the execution environments, for all the chains at the same time? That would be a much cleaner and more unified user experience. And then finally, shared execution is going to be around having the exact same safety as Ethereum L1, the EVM. So every time you create a new rollup, there might be a bug, there might be attack vectors like governance that can change the rules and can rug users. And what that means as a consequence is that we've lost fungibility, right? An ETH on L1 is different to an ETH on Optimism, which is different to an ETH on Arbitrum, because there's just different underlying security assumptions. And so once you have shared execution, you actually reestablish fungibility across the ecosystem. And another really cool thing is that once you share all of these four, you actually have shared forking, meaning that when the L1 forks, you also fork. So you have shared reorgs, synchronous reorgs, and you also have synchronous governance. So the layer 0, the social layer, can change the rules of Ethereum, and all the rules change at the same time. Imagine having like different modules, each of which is independently reorging, each of which is independently hard forking and upgrading. It's kind of really messy and requires maintenance. And this is one of the reasons why bridges are so brittle and so dangerous and get emptied on a regular basis. And when I see this diagram here, I think of network effects, and I just see network effects everywhere. And this is one of the reasons why I'm just so bullish on Ethereum effectively becoming the settlement layer for the Internet of Value, because there's such strong network effects that there's an opportunity for one layer to grab the lion's share here. And I believe that Ethereum has the capability from a scaling standpoint to have room for everyone. Okay, so now let's dig in specifically to shared sequencing. This is a topic I've been thinking about a lot lately. And this is this idea that different chains, different L2s on Ethereum can use the same sequencer. What does it mean? It means that at any given moment in time, at any given slot, there is a well-defined party who has monopoly power to order and sequence transactions for all the rollups that opt in at the same time. And what does it mean to share sequencing with the L1? It means that it's the layer 1 proposer who's already doing the sequencing for the EVM at layer 1 to also be doing the sequencing for these other chains. Now, one of the powers of shared sequencing is that it unlocks synchronous composability. So by default, if you have asynchronous chains, you have asynchronous composability. And this is good for some things, but it's kind of junky and awkward. And so really we want to have things happen at the same time. We want synchronicity. So one very basic form of synchronicity is synchronous inclusion, where you have transaction on rollup A, transaction on rollup B, and they both get included on chain at the same time. But we can do much better than that. We can actually have the transactions be aware of the state roots of each other. So you can have the post-state root of execution of transaction A, post-state root of transaction B, kind of read each other's state from the different rollups. But we can do even better than that. We can basically have the various rollups and L2s and execution environments send assets to each other immediately with no friction, all within the block. So let me try and visualize it. So today we have these silos. We have the layer 1 is its own silo, rollup A is its own silo, rollup B. And basically there's an opportunity to do magic. There's an opportunity for parts of the block, certain transactions, to be so-called super transactions. A super transaction is one that touches synchronously multiple execution environments. Now, if we zoom in to this section here where the L1 and rollup A synchronously compose, we have a super transaction made of 3 sub-transactions. So we have the first yellow one here, we have a green one here, and we have a yellow one here. And the important thing is that they're all happening at the same time, synchronously, and there's this notion of immediate transfer of assets. So you can have a token immediately be withdrawn from rollup A, for example, swapped on rollup B for cash, and then the cash goes back to rollup A. And all of this happens seamlessly, just like it happens on layer 1. So on layer 1, I could have a token and I just send it to Uniswap, and then I can go through Aave or some other smart contract, and all of this can happen synchronously. So in some sense, we're reintroducing what we've lost. And in some sense, we're trying to fix the fragmentation that the rollups have introduced in the short and medium term. And I won't go into the technical details, but basically there's several ways to do this. And there's a lot of recordings online that are now available. And 2 technologies that can actually enable this are, number 1, real-time proving. So it's this idea that you can prove statements about the rollups in real time with ultra-low latency. And the second technique is to use liquidity providers. So you can imagine the shared sequencer to provide liquidity and bridge any delays in the withdrawals that the rollups may have. Now, another really big advantage of shared sequencing is this idea of shared pre-confirmations, right? You have a single counterparty, and they give you a promise within 100 milliseconds that your super transactions will go through. So in some sense, we're trying to recreate the user experience of Solana, low latency user experience with synchronous composability on Ethereum. And the way that, and this is maybe like the biggest research unlock in the last few months in that space, which is that we can do it with L1 proposers. So we can have a subset of the L1 proposers put forward collateral and become sequencers and pre-confirmers. And so those would be like the L1 proposers that are in green here in the so-called look-ahead. The other proposers are just what we call includers. And the idea is that if I want a pre-confirmation, as a user, I'm going to talk to the next pre-confirmer who has the sequencing rights for all these shared L2s. And then I get a promise that my transaction will be executed such and such. And then we have the includer basically include and settle on-chain the transactions that have been sequenced as promised by the sequencer. Again, I don't want to go too much into the technical details, but the long story short is that we can have the L1 proposers provide sequencing services for the rollups. And this is kind of this somewhat lucky coincidence that we have this resource that can be used by the chains. And it's somewhat similar to call data. Call data is a little bit of an accident that it could be used for data availability by the rollups. It was not designed to be data available by the rollups, but it just so happens to be that it can be used as such, and it's the same for the layer 1 proposers. And in the last few months, there's been a lot of excitement for this notion of based sequencing. So we have Tycho. Yesterday, Aztec signaled that they might want to become a base rollup. Rise plans to launch as a base rollup. And there's this mystery like top rollup, one of the very top rollups in productions today that also aims to become a base rollup. And then we have all sorts of infrastructure builders and researchers and developers building stuff. And yesterday we had a whole Ethereum sequencing day with roughly 50 people where we kind of went through a lot of the technical details in order to achieve this vision. Okay, now the final part of my talk is a little bit more futuristic, but I think it will happen. This is this idea of shared execution. So today, if you want to build a rollup, you have to build your own custom virtual machine. Even if you want to be EVM equivalent, you have to build your own circuits, your own proof systems, your own fraud-proof game, whatever it is, and you'll have your own bugs, your own governance, and all of these things. And there's this little kind of hidden box in Vitalik's graphic of the roadmap, which is called Explore EVM Verification Precompile. And what that means is that once we've snarkified the EVM at layer 1, meaning that for every Ethereum block, we have corresponding snark proofs that these blocks are valid and they can be verified very efficiently, then there's a very easy next step, which is to expose within the EVM a precompile to verify EVM execution. So the precompile would take basically 3 inputs: a pre-state root, a post-state root, and a snark that this state transition between the pre-state and the post-state is valid. And then the precompile would return true or false if the snark passes verification. And this precompile basically allows you to build rollups and L2s that are equivalent to the EVM, not just simulated and like, let's hope that they're equivalent, but actually by construction, equivalent. And here, chains would be reusing and sharing the execution of Ethereum. But in order to get there, it's going to take several years because we need client diversity, just like we have client diversity of the execution clients. We have GEF and REF and whatnot. And because we're really paranoid in terms of security, we also want to do formal verification. And if any of you here are listening and are formal verification experts, please come to me because we're considering setting up some sort of very large prize, like tens of millions of dollars, to actually prove formal verification of EVMs and ZK EVM circuits. Now, once we have this kind of magical EVM within EVM precompile, then the barrier to entry to creating a new chain is extremely low, right? Because most of the heavy lifting technically to create a rollup today is around the verification game or the verifier circuit. We also have correctness by construction. So we have no more bugs. You can't, as a developer of a rollup, introduce a bug in the VM because it's literally by definition the EVM itself. And another really cool thing is that you have governance synchrony, meaning that anytime the social layer chooses to change the rules of the EVM and we have a hard fork, well, this EVM precompile within the EVM will magically upgrade at the exact same moment as the fork happens. And so now you don't need a separate governance token to maintain equivalence with DL1. And then the final really cool thing is that we can actually remove the gas limit. So why do we have a gas limit? Because there's this denial of service vector where we want the people running the full nodes and the validators to verify that blocks are valid within a reasonable period of time, within a few seconds, let's say. But once we have snarks, we can verify the validity of blocks in just a few milliseconds in this constant time. It doesn't depend on the amount of gas that was used. And so now we can remove the gas limit completely and basically be bottlenecked by the fundamental limits of physics and CPUs in terms of how much they can process. And this is basically, in some sense, a return of the vision of execution sharding. So previously, we had this idea of having 64 shards or 1,024 shards, each with a very homogeneous virtual machine. But here we have programmable execution sharding, meaning that anyone can trustlessly spin up a shard, and not only that, but they can customize it. So it's much more in line with the programmable nature of Ethereum. And not only is it programmable execution sharding, but it is like much more scalable execution sharding because we can remove this gas limit. Now, one question which is, I guess, worth asking is, what infrastructure will the chains not share? Like, what will be the customizations that are unique to every single chain? And I think there's a few of them worth highlighting. I think each chain has an opportunity to create its own brand, to have its own integrations, to have its own economy. So for example, Base has a very unique integration with Coinbase, and that's something that makes it very, very, very valuable. Another thing is that each rollup, even though they might choose to share the execution with the L1, they still have a lot of room on the tokenomics. They can have their own treasury, their own token governance. They can choose to do their own public goods funding like Optimism does. And they also have sovereignty over the value they create. So all the execution fees and all the MEV can accrue to these execution environments. And this is one of the big departures with the old roadmap of execution sharding, where all the fees would basically get burnt and go to ETH holders. Here, the idea of programmable execution sharding is where actually fees accrue to the developers and the L2s. And that's it. Thank you. If I have time, happy to take some questions.
We'll just do one or two questions if somebody has time, or if any questions. Sorry, we have a couple minutes. So, do you have any questions from the audience? One hand in the back. I'll have you kind of come up here and shout because we're not going to make sure the question is on the mic. So please move forward, and we'll give you the mic here.
Whoop. It's on now. Sorry. Maybe while we wait. Thanks a lot. And you mentioned already it's taking time. How long and what can we expect on the way there?
So one of the really exciting things about shared sequencing specifically is that it doesn't require any hard fork. And so it's just a matter of building the tooling and infrastructure off-chain, and it can happen incrementally. So you can have one rollup do it, and then another join in. And so this is a very organic thing. And in 6 weeks, Tycho, as I understand, plans to launch the first base rollup. And then a few weeks or months later after that, they intend to turn on pre-confirmations. So pre-confirmations does require a bit more work. And what I'm hopeful will happen is that Tycho will pick a really good pre-confirmation piece of infrastructure that others can just copy. And then some of these other chains, maybe Aztec, maybe Rise, maybe some other chains, can, once they see the benefits of synchronous composability, kind of join the party. One of the interesting things is around trying to measure the size of the network effects. And one of them is basically called Metcalfe's law, which says that the strength of the network effect is quadratic in the size of the network. Now, let's try and measure the size of the network using TVL as a proxy. The L1 set has $600 billion of TVL. And the largest sequencing environment is Arbitron's centralized sequencer, which has 15 or 20 billion. So there's more than an order of magnitude difference between the two. And so you'd expect the size of the difference in network effects to be at least 2 orders of magnitude. And I think we have this very cool and graceful plan now, which is, or at least possibility for assets, when they migrate from L1 to L2, they stay within this shared sequencing zone and they don't destroy the network effects of Ethereum. Because the current path where we're on, where each rollup has its own independent sequencer, is kind of chomping at the network effects and destroying it here while creating new ones. But the new ones that are being created are so much smaller than the one that we started with. Mami. Okay, question. Is there a plan for a shared constitution? So when you share the L1, there's this idea of shared forking, and part of it is that you're actually inheriting the social layer. And the social layer can, just change the rules as they see fit. And in some sense, constitutions are for humans. And so in some sense, yes, you are sharing this Ethereum culture when you choose to build on Ethereum. Whether or not we'll have a formalized constitution, I don't know about that, but maybe.
Hi, Justin. Is this on? So I guess my question is, so I see the upside of the shared sequencing and the collaboration, but it would feel like a shared sequence also maybe creates centralization risks, like between the protocols and, attack vectors. So I guess my question is, like, in the event of that, are there fallbacks that, the protocols can have to, like, remove these risks?
Right. So one of the common questions about shared sequencing is, are we not moving to a world where we have a super builder that's basically building blocks for all the rollups at the same time? And I think there's several answers to that. Answer number one is that we want to make sure that even hyper-centralized builders can't do harm on Ethereum. So we don't want them to be able to censor. We don't want them to be able to cause liveness or safety failures. We don't want them to be able to front run and sandwich. And it turns out we have technology to make sure that even the most evil, super builders can't do harm. So for example, for censorship, we have inclusion lists and encrypted mempools. And so I think it is important to be pushing these technologies in parallel to pushing the meme of shared sequencing. Another possible answer is that we have extremely high centralization of the building today, even for a single virtual machine, which can only process 20 transactions a second. We have 3 builders, Beaver, Titan, Rsync, that build 90% of the blocks. And in some sense, centralization is inevitable. And so we might as well kind of accept it. And the best thing we can do is be prepared for it. And then there's a final answer to this, which is that even if we have separate sequences for every single execution environment, we should expect layers on top to be built, which are basically collusion infrastructure for the proposers and sequences of these execution environments. And the reason is that if there is a non-negligible kind of value to be had from synchrony versus asynchrony, then now there's more of an opportunity to extract MEV and extract fees. And so you could imagine, for example, collusion infrastructure like Suave kind of being built on top and creating marketplaces for the sequencers to say, hey, if you want to buy up my sequencing slot at a premium, I'll just sell it to you. And in this world, we actually end up with more complexity and more centralization because the barrier to entry is higher precisely because we have more complexity to collude. And so if we just accept the most simple solution to unlock synchronous composability, which is just to have a single shared sequencer at every given slot, in some sense, that is the smallest barrier to entry that you could expect for the builders. Thank you.